You've built this huge following on social media, blowing it up. Is this what you do?
That's what I do. Yes.
So you have thought about what would excite them visually and intellectually. How much of this world is empowered by Chemist? Two new elements, when they come together and they make something new, can you predict its properties?
If you're going to rearrange atoms, likely you're going to need to break bonds and then make bonds.
What happens if I put a hunk of sodium in water?
Hydrogen gas is going to be evolved, which is extraordinarily flammable. It's an exothermic reaction, so usually it will ignite and you'll see a flame. Boom.
That's the chemist's way to say it'll blow up.
Boom. Yes.
Okay, I'm doing the experiment tonight.
Do it. You will feel it. You will feel it in your hand.
Tonight.
The experiment gauntlet has been thrown down.
Next time you make anything in your kitchen, just sit and reflect on the fact that none of that would happen without chemistry. This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. We got a Cosmic Queries edition coming, all about chemistry. More on that in just a moment. Chuck.
Hey.
How you doing, man?
I'm doing well, man. How you doing?
Okay. Who's that sitting next to you?
I got to tell you, only the most awesome chemist ever.
Ever.
Like, if you have anything called social media, then you have seen her conducting demonstrations of chemical reactions and explaining to you the wonderful world of chemistry.
Chemistry. Kate the chemist.
Yes.
Hi.
Welcome.
Hi.
Welcome to StarTalk.
Thank you.
And I need training on how to pronounce your last name. Bieberdorf?
Bieberdorf. Perfect. Yes. Bieberdorf. So like Justin Bieber and then Dorf. That's what I always say.
No, that's wrong.
The
You
alter
can't have
ego of his fan club.
it. That sounds like a fan club.
I'm a Bieberdorf.
Bieberdorf.
I'm a Bieberdorf. Are you a Bieberdorf? I'm a Bieber. I'm a
Oh, I like it.
Yeah, Bieber.
My students call themselves the Bieber dorks. So
Bieber dorks.
Yeah,
Good.
so I'll take
good.
that too.
That's good.
I like it.
that.
That's cool.
That's affectionate.
That's
That's affectionate.
I'm a Bieber dork.
So you're not just Kate the chemist
Right.
in your social media. You are associate professor of instruction and science entertainer. That's a thing. I'm glad that's a thing.
Yeah.
Why can't that be a thing?
That should be a thing.
You know, and associate professor of chemistry, University of Texas, Austin.
yes, hook 'em horns.
Oh, hook 'em horn. There it is. Okay. So you've built this huge following on social media, blowing shit up.
Yeah.
Is this what you do?
That's what I do. Yes.
That is so cool.
Wait, so how does that work on Twitter or in the medium where you don't have a video?
It's difficult for
Okay.
sure. I mean, you can share a video on Twitter
Yes, you
still.
can.
Yeah, but on Twitter, I try to be more academic, right? I highlight articles that I like or science.
Twitter X, excuse me.
Yes,
X.
apologies.
Yeah,
Yes, thank
X.
you. But highlight
Twitter.
good research or hot science in the moment. So it's easy to do that. But I will
Directing people.
correct.
Yes.
Yes, exactly. Or highlighting scientists that I like and saying, hey, you should follow this person or this person.
Okay.
But you are right. I mean, Instagram and TikTok are my big ones because it's very easy to get somebody to like you, breathe fire. I mean, that's just fun and visually appealing.
Yes. And so are these people who would not have otherwise been chemistry fans, do you think? And they're attracted to your clever way of bringing it down to earth?
But that's a compliment, so I will take that. But probably, yeah, I mean, honestly, most people hated their chemistry class. I hear that all the time,
among
right?
them, yes.
Both of you? Yeah, and that's terrible for me because it's my favorite thing. It's my absolute favorite thing. And so if I can...
By the way, anyone in your role who's also trying to do that with math has the same story. People hated their math class.
They don't have fire. I at least have fire. I have liquid nitrogen. I have
Right.
tools in my tool belt that I can use to get
Yeah, the math
kids
ain't-
excited about it.
They got nothing.
A calculator? It's not as
They
exciting.
can write pi
Yeah.
to 10 digits. All right. So you have thought about what would excite them
Right.
visually and intellectually.
Well, I was raised by psychologists. All of us agree on William James's theory of emotional memory. And so it's about if you have an emotional response to something, you're more likely to form a memory.
Absolutely.
So in the classroom, I can use fire. Like if I light my hand on fire, now all of a sudden the students are interested. And the research shows I have about 60 seconds to then teach
burn
them why
marks.
that
We're
works.
looking at her hand
Oh,
right
the
now.
research shows that
Yes.
rather than your life experience.
Yes. Also true.
That would
Yes.
also count as data, for sure.
For sure. Oh, for sure.
So you burning it like an alcohol or something in
No,
your
so
hand?
you dunk your hand in water first, and so
Yes.
you cover it. Water has a really high specific heat capacity, and so it takes a lot of energy to raise the temperature of the
Yes.
water.
So
So it
that's
acts
an
like
insulating layer.
Exactly. Yes, exactly.
Yes.
So it acts like a lab coat. Then you grab bubbles that have been pumped full of methane. Methane is very flammable.
Mm-hmm.
You hold on to it, you can light the bubbles on fire, and your hand doesn't burn at all, as long as you keep your fingers open. If you close your fingers or you're wearing rings, now you have a problem. But it's totally fine. But now the students are interested.
But just to be clear, methane, such as the gas that comes out of...
Cows. Is that what you're going to say?
Okay, cow.
Right. Cows. Let's leave it at cows.
Let's leave it at cows.
We'll leave it at cows.
It's a flammable gas.
Right.
So what you've done, at the risk of stating the obvious, is you've taken psychological research to turn yourself into a better chemistry teacher.
Yes, 100%. 100%. Yeah, I mean, the point, at the end of the day, my goal is for students to become good scientists. Only 5% of those students become chemistry majors. So I really want them to be educated voters. I want them to
You
be
mean in
able
your
to...
class?
In my class,
Yes.
yeah, my class. And so I want them to be educated voters. I want them to have quantitative reasoning skills, quantitative thinking skills. And so for me, it's all about building those skills through the lens of chemistry to try to make my students as smart, like the best citizens we possibly can have.
And how about your following? They just want to see stuff blow
Blow
up.
up.
More,
Or
yes.
they can become like chemical engineers.
Yes, that's for sure.
You must know because they'll write to you. Right?
Yes,
Yeah.
they do.
Yeah. So what do you know?
They like the explosions. They like the really quick, fast things. They do not want me to drone on about the structure of an atom.
But you never know when that will spark the curiosity that leads them to want to know what's behind that explosion.
Yeah, there it is.
You know, my son started off with just chemistry and liked it so much that he's going to school now for biochem.
You didn't tell me
Amazing.
that. You
Yeah,
didn't tell
he's
me
going to
that.
be a biochemist. That's what he tells me he wants to be.
You didn't tell me that.
Yeah.
great
And I
kid.
told him, don't be a biochemist. Own a biochem company.
Not a bad idea.
Let's get some basic chemistry on the table, okay? I can't claim to even know the answer to this myself. What is a chemical reaction?
Ooh, okay. So chemistry in general is the study of energy and matter and how they interact with each other. And so a chemical reaction is when you have a starting material, you do something to it, and you get a brand new product. So like if you're baking a cake, your reactants would be eggs, flour, sugar, chocolate chips, something like that. And then
okay.
you add heat,
You put chocolate
right?
chips in cake?
Yeah.
I don't know. I'm just making something
That's a
up.
waste.
Yeah.
Cookie.
Well, maybe you melt it, so it's a chocolate cake.
Okay, good,
Something like that.
good.
There we go. Okay.
A molten chocolate cake. Okay.
Good, that's good. That's good.
good.
Okay,
I'll
yum.
take
Okay,
that.
so then we have to heat it up, right? So you're going to put it in the oven.
So that's
and
an energy
then-
source
An energy source.
going into the cake.
Exactly. And then you're going to take it out and you have a brand new product. So a chemical reaction is you have starting materials, which we call reactants, and then you have a product at the end, which is the goal. That's what you're trying to produce, what you're trying to make, or what you're trying to study.
Okay, so now there are many things you can do that with, but then if you just wait long enough, this thing that you made turns into something else. Like
Like iron turning into rust.
Yes.
so other things can happen even after you're done doing what you're doing.
Oh, yeah.
So they would happen without your intervention.
Correct. So that goes back to being a spontaneous reaction. And so I'm going to jump into some thermodynamics. So pull me back if I go
Love me
too
some
far here.
thermodynamics.
Okay, okay.
Plus, I'm hearing these terms. It's easy to see now why people use the chemistry terms to refer to human relationships.
Right.
We had a spontaneous reaction.
Right.
Chemical was in our chemistry.
Yes.
Use your words, not my words.
They are my words.
Right,
Yeah,
right.
exactly.
Astro, we don't have that. Yeah, you got all the words for relationships. Okay. so go
Very,
on.
very fair.
Yeah.
So for a spontaneous reaction, this is a chemical reaction that will happen on its own in isolation. And so usually that's something that's exothermic. So it's going to give off heat as it goes from the reactants to the products. And it's usually something that has an increase in entropy. And so we know the second law of thermodynamics is to increase the entropy of the universe.
Yes.
And so if we have something that's exothermic, meaning it gives off heat, and then it has an increase in entropy, meaning the energy is spread out more so, that's a favorable reaction that would be spontaneous.
That's just the universe just being the universe.
Exactly. And
Without
that's
your intervention.
without my intervention. So that's a reaction that will happen on its own. So they don't even need me to do this.
Okay, so does the formation of diamonds count as happening on its own if that needs pressure and temperature and time?
That's what I was going to say. What are your conditions?
Yeah, okay.
So I would say yes over
I
time.
just can't put a lump of carbon on my table
And
come
wait.
back and wait for it to become a diamond.
Yeah.
Not for us. We will never see that.
Right.
Yes.
No.
But even though I did get a lump of carbon every year for Christmas, but that's okay. I mean, we're not going to get into that right now.
Sorry.
However, is it really happening on its own, or is the Earth actually providing the conditions necessary to make that reaction happen?
Great point. Absolutely great point. So on Earth, we refer to something as SATP or STP, so standard temperature and pressure.
Okay.
If we're talking about thermodynamics, that would mean we're at 25 degrees Celsius, so 298 Kelvin, and then 1 atmosphere. And so those are the conditions where it would happen on its own
25
naturally.
degrees
Celsius.
That's like a little higher than room temperature?
Yeah,
Slightly
it is.
higher?
25 is what we call room temperature.
Oh, I didn't know that.
Yeah, 25 C in chemistry, at least. That's how we define that. And so that's probably like, I don't know, 73, 75,
Yeah, it's a
something
little
like
above
that.
72.
Oh, 72. Okay.
It's a little above
73.
72.
That's what I said. Okay, cool.
Yeah.
Okay, and then at 1 atmosphere.
At 1 atmosphere. And
Of
that's
pressure.
Of pressure, right. And so that's how our chemical reactions occur here on Earth, because those are what our standard conditions are.
So I heard something. Is it beryllium? One of these elements on the periodic table in American charts is listed as a liquid, but in the UK it's listed as a solid.
But that's gallium.
Gallium.
I was like, beryllium.
Excuse me.
It's okay. Sorry.
Her voice was stupid.
No.
Right. So we talk about gallium.
Gallium.
So in the UK, it's listed as a solid because the room temperature in the UK is colder than here.
Wow.
And so it changes state at that point. So the conditions are everything. What you think something is
only what it is under those conditions.
Under those conditions.
Exactly.
That's it.
Yes.
Very cool. So one last thing about these exothermic reactions. There's also endothermic, if I remember correctly. So that's exactly what's going on. If you have a sore muscle, you get this pack and you sort of smash it and it becomes warm. There's another pack you can buy, you smash it.
And it becomes cold.
It becomes cold. So people like you has something to do with that.
Oh, thank you. Yes, I'll take credit for that. Absolutely.
Your people.
My people.
Your people. So you have special chemicals in there, which when combined, forcibly combined, will either absorb energy or emit energy or release energy. And so you have to know what those are in advance, obviously.
Oh, yeah, absolutely. And so usually how those things work is there's one pouch that's filled with something, and then there's another pouch in the inside. And so you're breaking the two pouches and allowing for the two things to mix.
Membrane between them.
Right, exactly. It's a really thin membrane, and just with a little bit of force, we can break it.
Okay.
What's neat for endothermic reactions is it's usually a salt that will dissolve in water. That's going to drop the temperature down. It's freezing point depression. And so that's what's going to be very, very cold, and we'll use it if you have an injury.
Right.
Okay.
And that's what they do when you make ice cream. That's why they use salt.
Yes. Oh, yeah.
Exactly.
That's correct.
Yeah.
Well, I think there's a different reason.
Really?
Yeah.
Why?
Yeah. I
If you make it by your hands, though, you add a little bit of salt for it so that you can go back and forth, yeah?
What do you make ice cream in your hands?
You put it in a Ziploc bag, and then you put milk and sugar,
and then
vanilla.
you can put it in a towel, and you put that inside of another bag of ice and salt, and then take the towel and just whip it
Here's what I'm
around.
saying. I'm an ice cream guy
Okay.
from way back.
All right.
I should weigh 100 pounds more, but I exercise just to wear off the
Just
ice
enough
cream.
to wear, just so I can eat ice cream.
Got your bucket, and it's filled with ice.
Right.
If you try to make ice cream that way, the cold of the ice is only pulling the heat out of the ice cream at the points where the solids are touching the rotating cylinder. Everywhere else is air. All right. You put salt on the ice melts at that temperature.
Right.
So now the medium is liquid.
And the liquid is now touching every single part of the
And it
cylinder,
is
but it is the
way
same
better.
temperature.
At the
It's
same
much
temperature as
colder.
the ice, correct.
Okay, that
And
makes
it's
sense.
way better at sucking the heat out than just solids that it's turning within.
All right. I'll accept that. Cogent argument you have made.
That's all I'm saying.
Which I should have known, because at first I was just like, all right, I finally got this guy.
No.
I'm like, I know for a fact that it's to lower the temperature, but that makes perfect sense.
Yeah.
That makes perfect sense.
So I would claim that salt in water does not lower the temperature. That's what I'm claiming.
Salt in water will always have freezing point depression. That is a thing. We can measure that.
No, I get that.
Yeah.
But if water's at a given temperature and salt is just the salt, I'm going to assert that you put the salt in the water, nothing happens to the temperature. That's what I'm going to claim.
False. Freezing point depression. It will go down. Delta T is equal to negative IKF times the molality.
By how
Mic
much?
drop.
By how much will it go down?
If you put salt in water, it goes down by negative 1.86 degrees Celsius.
Yeah,
It's molality, so it would be moles of solute divided by kilograms of solvent.
And does it matter what kind of salt?
Definitely. Yeah, it has to do with the Van Hoff factor.
Okay.
Yeah.
But at home you just have table salt.
Correct. And so it has a Van Hoff factor of 2.
So will this work for table salt?
Absolutely. Yes. Because when you put sodium chloride in water, it's going to break apart into the
Okay,
ions.
I'm doing the experiment tonight.
Do it. You will feel it. You will feel it in your hand.
I'm doing the experiment.
That is cool, man. I love
Yes.
it. The experiment gauntlet has been thrown down.
I promise you.
Okay. So how many degrees?
I challenge you,
think I can
sir. Ions at dawn.
2 Celsius max.
get? 2 Celsius.
Max.
Of what volume of salt?
I would make a super saturated solution.
Oh.
Yeah. So take a bunch of water, just dump salt in until you can see it at the bottom.
Yeah.
Stir. And you'll feel it. You will physically feel the temperature go down.
So I got to super saturate it. That's a lot of salt.
But don't do a lot of water. Just do a cup of water and just like you'll feel it.
Well, you have a huge fan base, and they heard you were coming on the show, and we solicited inquiries from them.
Exciting.
And what do you got here? I haven't seen them. Have you seen them?
No,
Nope.
we don't let.
Oh, yeah, okay. It's a loving group,
Yeah,
I promise.
they only ask things that they're really a great audience
Yeah.
and that are very curious and
Okay.
they ask
And they
great
pay for the privilege to ask a question.
Yes, they are our Patreon members, and so
No, just per month.
it's $5 a month if you're interested out there and
Which
you
is
want to
the
join
cheapest
Patreon.
membership of anything you would ever have. What do you
All
have?
right, here we go. This is Samuel Barnett. He says, "Greetings from London, England. Given the properties of molecules don't seem to match the properties of the elements they're made of. Example, water extinguishing fire despite being made of highly flammable oxygen plus hydrogen,
Right.
which we learned that's the big tanks on the rockets that take the space shuttle to space.
Yeah, the orange tank right
On
there.
the orange
visible.
tank, there it
Right,
is.
yeah, uh-huh.
So he says, is there a way to tell how a new molecule will behave ahead of time? Or is it just a case of suck it and see, or
I love that.
I'll say I'll clean it up for him. Trial and error.
Yeah,
yeah. Can
Okay.
you predict 2 new elements when they come together and they make something new? Can you predict its properties?
Yeah.
We will try to. So the periodic table is organized based on size, but it's also based on chemical properties.
Size meaning size of the nucleus.
Size of the whole atom.
The whole atom.
The whole atom, yeah. So including the electrons. And so when you look at a periodic table, if you go down a column, you would expect for every species in that column to behave similarly. So for example, if you go all the way to the far right on the periodic table, those are your inert gases, your noble gases. All of them have full octet shells, meaning they're not looking for an external valence electron. They're full.
They're happy in and of themselves.
They're satisfied.
There's got to be some psychological. You
Yes,
are
exactly.
content.
You're content.
It's very.
I really like it here. I gotta tell you, this electron shell just suits me perfectly.
I know. I don't need
I
anybody
don't know
else to
what
help.
it is. You know, I'm looking down at my nucleus. I'm just as happy as I can be.
That's it. There it is. The
Perfect.
right hand column personified by Chuck.
Yes.
Okay.
That's perfect. But you would expect everything. So like argon, neon, krypton, all of those gases to behave in a similar way. And so let's say you look at group 5, you've got nitrogen at the top, phosphorus is right underneath it. So you would expect for nitrogen and phosphorus to behave similarly. And that makes sense.
In a reaction, in a chemical reaction.
In a reaction if it's bonded to the same partners. So
Got it.
I would compare NH3 with pH3, and I would expect them to behave similarly, not the exact same way.
NH3, so that would be ammonia.
Ammonia
Yeah.
versus pH3 phosphine. And so we could compare the 2 of those and expect them to behave similarly. They each have a lone pair. They've got an electron pair available. So,
Interesting. That's
yeah.
a fair answer. I like that.
Oh, totally.
Yeah, yeah. That's,
You can predict it, but then you test it.
Right. You predict it and then you blow something up. Like,
yeah, but I bet
Safely.
people before you understood the periodic table, there must have been a lot of trial and error.
Of course. But there still is. There's still trial and error. You have a guess. You want to use your money the best you possibly can. You only have a limited funding. So you want to put your eggs in the best basket.
Yeah.
So how about now? There's something in AI, I believe it's called offline reinforcement learning. And so what that does is the AI observes a bunch of things similar, and then it makes predictions based on what it's observed. Do you guys use anything like that to figure out?
That's the definition of science. That's what we do.
Duh.
We stare, right? I mean, right? We watch something. We try to detect patterns. That's all we learn in
Except
grad
we
school.
don't use AI. We use NI, natural intelligence.
Oh,
Nice.
okay. Right on.
Fist bump.
I'm going to say That's a little more rare.
All right, next question. Who do you have?
All right, this is Mike Muhammad Kaki. He says, greetings, Dr. Tyson, Dr. Bieberdorf, and Lord Nice. Mike Kaki here from Berlin, Germany. Can you explain the role of activation energy in a chemical reaction and how it influences the rate of reaction?
I love that.
That's a beautiful question.
What is activation energy?
So activation energy is the minimum energy required for a chemical reaction to occur.
So it's sitting there otherwise happy
Yeah.
until you put energy in it, then it runs away?
Yes, sometimes no. It kind of depends on the conditions and what else is going on in the environment. But in general, if you're going to rearrange atoms, likely you're going to need to break bonds and then make bonds. And so activation energy is that minimum energy required to actually rearrange those atoms.
In whatever way is your intent.
Right, exactly. And so it's based on the collision. And so the orientation of the molecules matters. If you need them to hit head on and then they do like side by side, you might not have the collision.
Wait a minute. You know how the molecules are oriented?
Well, we know that what orientation, what collisions are favorable. And so we know if these two atoms need to interact and form a bond, if you have the molecules slap each other from the other side.
So do molecules have like docking ports, basically?
I'm okay with that.
Yeah, what I'm saying, yes, but how do you configure them to know which docking ports are pointing which way? Aren't they littler than you can see?
Well, sure, but you know that if you have one side of the molecule, like let's say I'm a molecule, and I know that my right hand needs to form a bond with your right hand. If our left hands collide, we're not going to form a bond because those aren't favorable interactions.
But how do you control that?
We can't.
Oh, okay.
No.
That's what spooked me.
Oh, no.
I thought she's up there with tweezers, putting one molecule.
That's the dream. I would love that.
To another. All right.
No, we can't because it's usually in solution or in gas phase, so the collisions are not. Yeah, we can't control that.
Okay.
No, but what has to happen is they have to collide with enough velocity, so kinetic energy, to overcome the potential energy push away. So the
that would count
proton
as an activation energy, the speed.
Correct.
That they collide.
Part of it. It's part of it.
Okay.
All of it. And so you have to have the energy coming in that is stronger than the proton repulsions that are happening between the atoms, and it has to be at the right collision. All of that is kind of looped up into activation energy.
And can you know that in advance, like from equations, or will you measure that?
100%. Yeah. So you would use an Arrhenius law. So it's the natural log of rate 1 over rate 2 is equal to your activation energy divided by R times 1 over T1 minus 1 over T2.
Arrhenius.
Wow, you are good at this.
I had to find it.
This is like way back.
Way back. Yeah.
Arrhenius.
Yeah. And
when was Arrhenius?
Ooh, I don't know. I couldn't give you a year.
Long enough ago that nobody is named Arrhenius. That's how long ago it was. You have never met an Arrhenius in your life.
And Arrhenius doesn't even have a middle or last name. It's just
It's like
Arrhenius.
Cher. I'm Arrhenius.
I love that.
Yeah.
You know what I'm trying to figure out, though, that some reactions are just so favorable or so common. Can you take what you said and I'm lighting a piece of paper on fire, which is a reaction that everybody knows. What would be happening there from what you just explained?
I would say the activation energy was the match. I'm spitballing here.
Part of it.
But
Just
I'm
saying.
thinking,
Yeah.
I'm just saying.
So if you have a fire, that's a combustion reaction. So you have a source of fuel, you treat it with oxygen, and you produce carbon dioxide and water. And so what you're doing is breaking all of the bonds in the fuel and the oxygen, and you're rearranging it to form carbon dioxide, CO2, and then H2O. And so it's all about literally pulling these species apart, pulling the atoms apart, and then allowing them to rearrange and form a new bond.
And is it, based on what we said moments ago, is it fair to say that whatever's the configuration of the molecules in the paper, the configuration afterwards has lower energy? Because all that energy became
you
in the
release
fire.
the energy,
right? Is that a fair?
fire.
Did I say that right?
If it's favorable, yes. If it's favorable, you're going from higher energy to lower energy.
Yes.
But if we had to force that, if we were in like extreme conditions to make this happen, then not necessarily. You can force things to go higher energy, but usually
at
for what
the
you're
cost
saying.
of putting the energy in.
Correct.
Yeah. Okay.
Yes.
Okay.
Exactly.
All right. That was cool, man. Thanks a lot.
Can I do one clarification,
Yeah,
though?
please.
Okay, so activation energy is about kinetics. Kinetics is the study of time. Thermodynamics is the study of energy. And so when we're talking about exo and endothermic, that's talking about the energy transitions. You're going from high energy to low energy, exo, low energy to high energy, endo. That's thermodynamics. And so that's, will it happen? Is it possible for this reaction to occur? Kinetics is how long. And so activation energy is really a measurement of how long something's going to take. So you need enough energy, and it can guide us to figure out rate constants. And so often people combine these two things, but it's, will it happen is thermo. At all. And then how long. And so from a standpoint of like going into lab, I care about kinetics. I want to know how long my reaction is going to take. Because can I go home? Do I have to stay here all night? Like, so kinetics actually matters. So that's why people care about activation energy.
So you want the experiment to be done before you go to sleep?
Yes. Or
before you die.
Right. Or you can set it up and then go home and work it up in the morning. That's best case scenario.
Okay. All right. This is Lawrence Harris. And Lawrence says, good day, gentlemen and gentle lady. What is happening when you raise sugars to the candy temperature? It starts as a liquid, becomes a soft candy, but if you keep raising the temperature, it will eventually become hard.
What's up with that?
What is going on there? And by the way, worst candy ever.
And also, there it is, a liquid, and you think, oh, let me just taste that.
Oh,
it's like, whoa,
look at
that's
that.
way hotter than boiling water.
Look at that. I burn not only my finger, I don't have a finger, I have no tongue. I hate candy now. This is just a disaster.
I hate
this
chemistry.
Is terrible.
So we talked earlier about dissolving salt in water,
Yes.
And it's a very similar thing. So you're going to dissolve sugar in water. They're going to form intermolecular forces, and so that's going to dissolve the sugar crystals with the water
Will
molecules.
that also drop the temperature?
In the beginning, yes, but it's not going to be as much because it has a Van Hoff factor of 1. It doesn't break apart.
That's somebody else.
Yes, that's somebody else.
Some other chemist of the past.
And so for the ionic species, when you put them in water, they break apart.
I want a Biebdorf factor.
You nice. I don't have one.
You don't have
I
a
should
factor?
have one. No.
You can't hang unless you have a factor.
I know. All right. Well, next time. I'll have one by the time we come back.
All
but
right.
for sugar, you're going to dissolve. In theory, it would decrease your freezing point, but it's not going to be much because it's a covalent species. In the same breath, when you put sugar in water, it's going to increase your boiling point. And so that's why you can get that temperature a little bit hotter because the sugar is there to kind of mess with that. So what's interesting about sugar is that when you heat it up, it's going to dissolve. You're going to increase the solubility. And so
That's true for anything.
for anything. Yeah.
Right.
Well, it's true for salts and solid solutes. But if you use a gaseous solute, you increase
no,
the temperature,
then
it
it comes
decreases.
out.
Yeah, it's the other way.
So if you boil soda, then the gas just comes out. It doesn't stay dissolved in. Right.
Boom.
Got it. It's
Yeah,
the opposite.
it's the opposite, exactly. So when you add sugar in, you're going to heat it up, and then it's going to dissolve. And so that's why you heat it. But it's the cooling process that really dictates whether or not you're going to have like a smooth candy or the hard candy, like rock candy. So if you don't touch it at all, you're going to allow for your system to kind of minimize the entropy, lock into these beautiful cages.
Give it a chance to do it all by itself.
Exactly. Yes. Let it settle. And then you'll get these gorgeous rocks on, and you probably have to put like a stick in there, but you'll get those rock candies that are typical of rock candy. But if you mess with it while it's cooling down, if you stir it, if you kind of shake it up a little bit, you can't form those gorgeous crystals. And so you're not going to get rock candy. You're going to get something closer to like fudge. And so it's a lot smoother. And so it's really, in my opinion, all the cooling process and like how are you allowing those crystals
So
to
it's not
form?
how you heat it, it's how you
cool it.
That's my understanding.
No, that makes
Yeah.
sense. My mom used to make candied sweet potatoes.
Oh.
And the way you start the candy process is, and they call it candy, it wasn't actual candy. It's a sweet potato with a sugar coating. But the way you start it is you just take regular table sugar, you put it in a pan, and under a low but intense enough to melt heat, you bring the sugar slowly up to a temperature.
Just pure sugar.
Just pure sugar.
No water, anything.
And no water, nothing. But you can't do it too fast because you'll just burn the sugar.
burn the sugar.
But what happens is the sugar very slowly, as you watch it, you can see it from the bottom, as wherever the contact with the pan is, it just kind of splays out and becomes brown and caramel-like, and it slowly becomes this kind of gooey, like caramel-like sugar. And then, depending on how you cool it, or you do something to it, you stir it, whatever, but then it becomes like a syrupy fudge. And then when it cools, it just becomes like a little like caramel coating over top of the sweet potato.
So your kitchen was a chemistry lab.
Oh, definitely. Let me tell you something. It was one of my favorite things to watch.
So kitchens are the thing.
Yes, every kitchen is a chemistry lab. Thank you for making my point.
Yes. Because it's just I need some of this and some of that.
Yes, you're
and
cooking.
it's all
your
lined up
chemistry.
for you
Yes.
in all the cabinets.
Yeah, I didn't think of it until now, but that's absolutely
Especially baking. Baking for sure is chemistry. Cooking is also, but there's a time component. You can have fun with it. Baking is precise.
Very
you need to
precise.
be exact. And
Right.
Yeah. So
No,
the ratio's
but
important.
if you take albumin from an egg, which is otherwise transparent, then you heat it. Not many things will you heat do they then become solid, but the colorless part of the egg becomes solid.
Yeah.
That's kind of weird.
right.
Well, it's all about those proteins, right? I think they're opening up and then they
Okay.
can form bonds between each other.
right.
So I've seen this done, and I thought it was magic, where if you take sweetened condensed milk, okay, and you boil the can closed for like an hour, then pressure builds up in the can, and then you come back and then you open it, and it's like caramel pours out.
Wow. Okay.
You haven't done that?
I have not done that.
Oh my gosh!
I'll try that.
I thought it was the experiment. The chemist hasn't done yet.
No.
So sweetened condensed milk,
Okay.
okay?
So it must have a really high sugar content.
Yeah, 'cause
right?
sweetened and it's
yeah,
condensed.
and it's condensed.
Yeah, you use it for things like key lime pies and
All
things
kinds of baking.
Like this baking.
Like
Yeah,
super
oh, yeah,
sweet baking
yeah.
stuff.
where you need the milk, but you don't need as much milk.
Sure.
So you'd have a reduced milk.
It just must have a lot of sugar though, if it's able to turn it into essentially
Yeah, but
the
with the
liquid
milk.
candy.
With the
yeah.
milk, it's not just.
So it's a fat piece, so that must give it like the creaminess or
yeah.
something.
Oh my
Ooh,
gosh!
fancy.
When I saw that done and they opened the can and poured, I was like, no, wait a minute now. Come on now. I thought they were.
I don't know. I think that's how they make dulce de leche, but
That's what I'm saying.
Yeah, I'm pretty
It was
sure
very
that's
dulce de leche.
Yeah.
Yeah.
It's pretty cool.
That sounds
Okay.
good.
All right, here we go. This is Caleb Lillard, or Lillard, if the double L and he's Spanish, who knows?
Caleb surely knows.
Yes,
Okay.
exactly.
Go ahead.
Caleb says, "Good day. This is Caleb Lillard from Dallas, Texas. Considering the increasing attention being given to the awareness of PFAS chemicals and how prevalent they are in everyone's lives, I honestly was just wondering if what is being spread through typical means of communication is more hyperbole, or if it should be associated with the level of gravity with which it has been paired." All right, so anyway, this question goes on, but really what he's saying is this. Are PFAS as dangerous as we think they are?
Are these things that never go away in the environment?
Right.
Yes,
That's the problem.
exactly.
Yes.
I heard about it, but I don't know anything about it.
They're called forever chemicals. Is what
exactly.
they're called.
And what is the acronym for?
So it's per and polyfluoral alkyl substances.
Okay, let's keep it at PFAS.
PFAS, yeah.
Duly abbreviated.
Yes.
Right.
But
PFAS.
the big piece is they have a carbon chain as the backbone, and then they're connected to fluorine.
But
And
wait a minute, doesn't everything have a carbon chain?
a lot of things, not everything.
Aren't we just carbon chain?
Yes, we are just carbon chains too. But for PFAS, they've got this carbon backbone and they're connected to fluorine, and they're really strong carbon fluorine bonds, really strong. And so that's what make them forever chemicals.
Because they can't be broken down.
Not easily.
Not easily.
Not easily. And so
or
if
it
you,
takes a long time to
Wait,
break
so
them
those
down.
chlorofluoro,
carbon
carbons.
CFCs.
that's fluorocarbon, it's in there too.
Chlorofluorocarbon. So that usually is a much smaller molecule. And so it's
Okay.
like my memory is that there's carbon
These are
and
the
then it's
ones that
attached
were
to a couple things.
from the refrigerant.
Right.
That,
It's
The ozone
that
hole.
killing the
hole.
ozone.
Okay, so I'm confusing the two.
It's okay.
Go ahead.
So, but that's good to clarify the difference. So CFCs are much smaller, but they also are bad for the environment. They're gases. So PFAS here are much bigger molecules. And so if they get into our body, because they're forever molecules and we can't break them down as easily, they stay in
stay.
our body.
Right.
And so that's what's a problem. And this
Just
is
to be clear, you have to quantify for me. How big is a big molecule?
well, it ranges, and that's the problem. So there's 15,000 different molecules that can be considered a PFAS. And so that's the problem with this. It's really a generic term.
That's
At the end, we're just PFAS chemicals.
yeah.
it
I'm
sounds
going to
like.
say that's not hyperbole.
It's not
That
hyperbole.
is scary as hell.
Yes, and it's particularly troubling for women. We know that it causes fertility issues. We know that in young women, so teenagers or girls who have yet to go through puberty, it is causing a delay in puberty. So we're seeing that issue coming up.
But why can't we just poop it out?
Well, I think it's because it sticks with inside of our body. It must be forming some kind of like intermolecular force with the inside of our body, and so it's strong enough. Because I wouldn't be surprised I'm speculating, but I wouldn't be surprised for fluorine to easily form some kind of intermolecular force with something in our body. They have 3 lone pairs on them, so it's really
Through
easy.
the digestive tract, it
Something,
gets
yeah,
absorbed in.
anywhere.
Okay, so
Yeah.
is it hyperbole? And where did wait, back up. Where do these come from?
They are generated. We make them a lot of times. Yeah, I would say actually, I think all the times we
On
make them.
purpose?
Yeah.
For what?
Plastics, basically. Linings inside of bottles,
So we're killing ourselves.
basically.
That wouldn't be the first
It's-
time this has been a thing.
We have a pattern.
We have a pattern. We're sensing the pattern. All right. So it's in the environment.
It's in the
We
environment.
ingest it, and they never leave our bodies.
In theory, right? And I'm sure the smaller ones probably you can leave, but if the bigger they are, the more likely it is for them to form a bond inside of our bodies. And so it's problematic. Am I going to try to eat PFAS? No. Am I going to try to avoid it? Yes. And so I don't think it's hyperbole. I think we really should avoid it.
Okay.
Wow.
Well, good question.
And if it's plastics and linings, there's no FDA label for PFAS, so you have to just read articles that highlight it, right? So what's the biggest source of PFAS into our system?
Well, I don't want to point fingers, but a lot of times it has to do with chemical waste, right? And if we're not disposing it properly, then it can get into our
okay,
water
water
system.
supply.
Why don't you want to point fingers?
Well, I mean, I should point fingers.
Because those companies are chemical companies.
Yes.
I'm just saying.
Because they'll point their finger back at you.
And I want to get hired. I'd rather be on their side and then advocate for good science and maybe
Right.
help them fix the
Got
problem.
it.
So that
Rather
I
than-
want to be a chemical
rather than
advocate.
play a blame game.
Correct. Yes.
Yeah,
I want to
right.
help.
There's two different tactics.
Correct.
Yes.
Yes.
Yes. All right.
Right. Okay.
Well, thank you for that.
That's a good question.
Yeah, so this is Alan Rayer. Alan says, hello, Dr. Kate. Privileged to follow you on Instagram.
Oh, thank you.
There you go.
It's Alan from Lithuania here. What gives colors to the elements? Why does the color change in an element based on molecular bonds?
Ooh, I love
Okay.
that.
So couple different answers here. It depends on the context of the question and what we're specifically looking at. So if we're looking at metals, just a generic metal in the neutral state, when we have an excitation, our electrons are going to move. They're going to go up in a level. Think stairs. So they're quantized energy levels. So the electron will literally drink a Red Bull and then run up a bunch of stairs. That process is normal. But when they fall down the stairs, just like if we as humans fall down the stairs, we're going to scream and release energy. Electrons do the same thing. So as they fall down these steps, these quantized energy levels, they release energy in the form of visible light. And so if you have a big gap, you're going to see a high energy light, blues and
But
purples.
is that what he's asking? Was it more simple, just different things have different colors? So
But that's why,
rather
though.
than glowing, that's a glowing metal, right?
It's an excited metal giving off light. Right?
Like tungsten.
Okay, but yeah.
Well, that's thermal, though.
That's thermal,
rather than
yeah.
That's different. Yeah. So, okay,
electronic.
but like what about a quantum dot? So a quantum dot is something where if it's really small, like 2 nanometers, we're going to have a color of blue being emitted. But if it's a little bit bigger, with 6 nanometers, not that much bigger, we'll see
It'd
a
be
color
red.
of red.
Yeah.
Yeah, exactly.
Oh.
And so
That's the
there,
wavelength of the light
That is giving
that
off.
would
That's
be-
really wild.
so
Get out of here.
yeah, that's how I think about it. Is how just like it's emitting light, and that's the color we see. So that's the context.
So what about all the things that are colorless?
Oh well, they are not emitting
Or just
something.
white, like salt and sugar
Sure.
and flour and, there's so many things that just have no color.
Well,
The kitchen would be so much more interesting.
no color that our human eyes can see. We only see the visible spectrum, so we can see from 400 to 700 nanometers.
That's physiology.
But if it's outside of that,
With
we
your
don't see
stupid
it.
human eyes. Your big, dumb human eyes
dumb-
can't see
dumbass.
anything.
way she said it. Damn.
It's true.
She acted like she could see outside that spectrum and the rest of us can't.
I can't.
All right, keep going, Chuck.
All right, this is Daniel Gilligan. Daniel says, greetings, friends. Daniel here from Tasmania, Australia. Okay,
What was that?
that was my Tasmanian devil.
Really, is that even allowed anymore?
He says, how come water isn't the most flammable thing in the world, especially salt water? As separate elements, oxygen, hydrogen, and sodium are all very spicy when it comes to being flammable or dangerous.
Wait, so let's start this off. What happens if I put a hunk of sodium in water?
Oh, you're going to see hydrogen gas is going to be evolved, which is extraordinarily flammable. It's an exothermic reaction, so usually it will ignite, and you'll see a flame. A boom.
That's the chemist's way to say it'll
It's
blow
gonna
up.
blow
Boom. Yes.
Lot of
Okay,
yeah.
that's sodium, and sodium is in sodium chloride, salt. And then we know
But they're different. Those are different. Sodium that you throw into the water is a chunk of metal, and that's an oxidation state of 0.
Okay.
But sodium chloride has an oxidation state of +1. And so the short answer to the question is, where are the electrons next to these atoms? And so it's how they're sharing them or they're transferring the electrons is going to dictate how they're going to behave.
So
This is unbelievable stuff.
wait,
It's like-
so the molecule, you cannot infer the property of the molecule from the properties of the atoms that go into it.
You can, if it has the same, if you're comparing like apples to apples. So if you're comparing CO2 versus SiO2.
That's one way.
That's one way you can compare it.
However, I'm saying, like the questioner said, we know hydrogen is flammable.
Right.
We know oxygen feeds flames. You put them together and it extinguishes flames.
Yes.
That's weird.
It is weird, but they're so different though, because hydrogen is H2. It's two hydrogens bond together, so they're sharing 2 electrons. You've got oxygen has a double bond between it, so they're sharing 4 electrons. That's a really strong bond. And then water has 1 oxygen and 2 hydrogens. Those hydrogens are not next to each other. The oxygen's in the middle.
Separated.
Yeah. And oxygen is the second most electronegative atom that we know about, meaning it pulls the electrons from its species. So in hydrogen, the electrons are being evenly shared. In water, most of the electrons are completely up on the oxygen. And so it's all about where the electrons are in the reactivity.
So oxygen steals electrons
Every time.
Like no matter. It's just
Like it's nobody's
basically
business.
it's a thief. Like don't bring your girl around oxygen.
That's the perfect
'Cause
analogy.
Don't bring your girl around oxygen. We know the deal. Oxygen is like Michael B. Jordan. Your woman is leaving with him tonight.
Yes. That's exactly it.
Okay.
I'm going to use that in my classroom, by the way.
Okay.
Wow.
So Kate.
Yeah.
I understand that you have a podcast.
I do.
An NPR podcast.
Yes, Seeking a Scientist. We just dropped
all the right investments and anything going into it.
Yes, exactly. So we just dropped season 2, and our first episode of season 2 was about being in space. It was the DART mission. We interviewed Nancy Chabot.
Double asteroid redirect test.
Yes, exactly. And so we go through the entire process from the beginning of the creation of the experiment all the way to now what's happening and what their future missions are planned. It's awesome.
So these are scientists active in something that you might be interested in as a listener.
Yes, and I would someday love to have a chemist on there, but yet it's been completely other than chemistry. Like we're talking to someone who studies dogs and how you pick.
Ask a chemist, it's just ask a scientist.
We're seeking a scientist
from any field.
Exactly. We've got this one woman who's doing research on puppies to figure out how you can determine what is the best service dog. Like that's her research, is figuring out how to predict that. So we interview her, and so that's coming up in a couple weeks.
The answer is it will not make a difference because in 10 years, all service dogs will be autonomous robots that actually just guide you.
Oh, I love the golden retrievers. I want them to stick around.
Yeah, guess what? Robots don't poop.
Not yet.
Not yet. So it's filmed in your hometown, where you are in Austin?
Yeah, I film out of Austin, and we interview scientists from all across the planet.
Wow.
Okay, so they'll virtually.
Virtually, yeah, it's all virtually, but the host city is actually Kansas City, so I got to give a shout out to KCUR.
Okay.
KCUR, okay. As in the public station model.
Correct.
It's distributed. It's not one central creating point. And so they create it, and then it's shared with other stations.
Yep.
All right. Well, Kate, it's been delightful. Finally, we met over the internet, but not in person. Thanks for coming by.
Thank you for having me.
And
It's so
sharing
wonderful.
your media calendar with us here.
Thank you.
All right, Chuck, always good to have you, man.
Always a pleasure.
All right. In conversation with a chemist, which doesn't happen to me often, I'm just reminded how much of this world is empowered by chemists. What they have done for us has transformed our lives in every measurable way. Yet, at the end, it doesn't say, by the time you use your cold pack, when you're done and your knee is a little better from this endothermic reaction that a chemist put in here, thank your nearby chemist. No, there's no such instructions there. We just do it and take it all for granted. I should have a conversation with a chemist more often so that I take less of what happens around me for granted. If you don't get to have a conversation with a chemist, next time you make anything in your kitchen, just sit and reflect on the fact that none of that would happen without chemistry. And that's a cosmic perspective, not only on the universe, but on your everyday life. Keep looking up.